afternoon. Good afternoon to this week's edition of the Heidelberg Joint Astronominal Colloquium. It's a great pleasure to announce Suyu from NTA in Garching, talking about shedding light on the dark cosmos through gravitational lensing. I think we hardly had ever such a lyric and nice topic and title. So we are all very curious about the latest results of using lensing to unveil the large-scale structure of the universe. Before we start, a few words on Sherry's CV as a scientist. She started in Queen's University in Canada with a bachelor, then she moved further south to California to Caltech, where she received her PhD in 2008. Then she went to Germany to the Anomalous in Bonn. From that, she moved back to California to Santa Barbara. So we must enjoy the Pacific by then, fully agree. Then she moved to the Asia Institute in Taipei. And since last year, she is Max Planck Fellow at the Max Planck Institute for Astrophysics in Garching, with a joint appointment at the Technical University of Munich. So, welcome, Sherry.
I'm happy to tell you about shedding light on the dark cosmos through gravitational lensing. So in the past decade or so, a standard cosmological model has emerged, namely the flat lambda CDM model, where our universe is spatially flat and composed of mostly dark energy, described by the cosmological constant lambda, and cold dark matter CDM. So this lambda CDM model fits very well observation on the large scales, including the cosmic microwave background. However, there's still several puzzles that remain in cosmology. In particular, what is the nature of dark energy and dark matter? Is our universe spatially flat? How many relativistic species are present in the early universe? Measuring the Hubble constant, which is a key parameter in our cosmological model that tells us the current expansion rate of the universe, actually provides a way to address these questions. So the Hubble constant, or also known as H0, sets the age, size, and the critical density of the universe. And it gives us the present day expansion rate, V equals H0 d, so a galaxy at distance d is moving away from us at velocity v, that's given by that equation. This is the Hubble's law. And the Hubble constant provides critical independent constraints on the nature of dark energy, neutrino physics, and spatial curvature of the universe. Shown here is a figure taken from Adam Rees's recent paper of recent measurements of the Hubble constant. So this point here, this is the measurement of the Hubble constant from the Planck satellite that observes the cosmic microwave background, CMB, assuming flat lambda CDM. This point here is from other CMB experiments, particularly the Wilkinson Microwave Anisotropy Probe, South Pole Telescope, Akatama Cosmology Telescope, and Baryonic Acoustic Constellations, again assuming this flat lambda CDM model. And here, these points here, these are more direct measurements of the Hubble constant without having to assume the flat lambda CDM. So these points here are from the local distance ladder. So this is getting Hubble constant by measuring distances to set fields, and then using that to calibrate distances to supernova and see how fast we receive from us. So this is the distance ladder. This is the infrared television. This is gravitational lensing, SD cluster, and water meters. So most of these direct measurements are actually high in comparison to the Planck measurement. So this tension, if it is significant, would actually indicate the physics, because this point from Planck assumed that the cosmology is flat lambda CDM. And if we go beyond the standard cosmological model, For example, if you have a dark energy equation of state W that is different from -1, or different from the cosmological constant, so if it's more negative, then the H naught from Planck would actually increase, as indicated by these arrows. Or if the number of relativistic neutrino species is higher, H naught from Planck would also become higher. And similarly for the spatial curvature of the universe. So if this tension is real, then this means that our universe is not the standard flat Laplacian, and we actually need something more. So this would be new physics, and to test whether there is indeed new physics, we need more precise and accurate measurements of the Hubble constant, because currently, the tension is almost 3 sigma, but we need actually independent methods, especially to overcome the systematics, especially the unknown unknowns. So one particular method that I will focus on in this talk is gravitational lensing. So shown here is an image illustrating the effect of gravitational lensing. Suppose we have a background star here. So as its light ray approaches the sun, the light path will get deflected due to the gravitational field of the sun, so that it comes to us on Earth here, and we see the light of the star to be observed here, straight line, instead of this original position. So this is the effect of gravitational lensing, the bending of light due to the gravitational field, in this case, of the sun. So the gravitational lensing is actually not too different from lensing that we're used to in everyday life. So shown here is an example of optical lensing. So suppose we have a candlelight, and we put the base of a wine glass in front of it. Then what happens is that we can get multiple images of the candlelight. So shown here is 1, 2, and 3, and that fourth one behind the stem. So this is strong optical lensing, where we get multiple images of the same background source, or the same candlelight. And if we change the tilt of the base of the wine glass, we can get different image configurations. So shown here is 2 images. And if the wine glass is perfectly aligned along the line of sight to the background source, we can actually get this nice ring. This is the Einstein ring, and the radius of this ring is the Einstein radius. So the next time you're at a wine party, you can give this a try. And I promise you, you'll actually see this before getting drunk. So strong gravitational lensing is not too different from strong optical lensing. So what you need essentially is to replace the background source, the candlelight, by an astrophysical source like a galaxy, and the wine glass by a massive galaxy that can bend light, such as a massive early type elliptical galaxy there. So if you do this, you get this kind of system. This is a gravitational lens system observed with Hubble Space Telescope. So this bright thing here, this is the lens in a massive elliptical lens galaxy, like the one glass we have here. And a background source galaxy that is blue is lensed into 4 images, 1, and 2 and 3 are merging here, and the fourth one there. So notice that the configuration of this image is actually very similar to the one that we saw with the wine glass. So some of these strongly lensed systems are special in that the background source galaxy has intensity that varies over time. So this is an example of such a system. So this is 1608. A background source galaxy is lensed into A, B, C, and D image by 2 foreground galaxies G1 and G2. And what's special about this one system is that the background source has an active galactic nucleus, which is called AGN. So an active galactic nucleus is a supermassive black hole at the center of the galaxy that is accreting material onto itself. And as the supermassive black hole accretes, it emits radiation, and because the accretion is not uniform, the radiation emitted changes over time. So if we observe this system over time, we will see each of the 4 images shown here of A, B, C, and D. So these are the 4 images. You see that they're flickering And that image B brightens up first, followed by A, C, and D. So the flickering pattern, each of the images, must be the same because they come from the same background source. But they're delayed in time because the different images, they take different light paths. So image A would take this one, and image B would take this one. So the two light paths have different path lengths, so there's a geometric delay. And also the gravitational field of the lens act further, and it leads to a gravitational delay. So the combination of two delays is what allows you to see the delay between the brightening of the images. So shown here is the relative image flux as a function of time in days, so image B flickers, but at some point it brightens and followed by A, C, and D. So the expression for this time delay is actually quite simple, as shown there. So T is 1 over C times D delta T, this is the so-called time delay distance, times phi length, which is a Fermat potential related to the mass distribution of the lens. So this time delay distance is actually a combination of the three distances that we have in lensing. So we have us, lens, and then the source. So there are three distances. There's the distance between us and the lens, and then there's the distance between lens and the source, and distance between us and the source. So this time delay distance is actually a combination of these three distances in lensing. And by construction, because it's a combination of these three distances, is actually mainly sensitive to the Hubble constant. It's inversely proportional to it. So for this kind of system, if we can measure the distance, we can actually constrain the Hubble constant. So all our cosmological information enters here. So to measure this distance, we need three things. So you can see from this equation, we need to know the time delays. That's the first thing. Second one is we need to know the lens mass distribution, that is of these two galaxies GW, because that affects this potential here. And then the third one is we need to have some knowledge of the structure along the line of sight to the source that can perturb all this Fermat potential. So if we know these three things, we can get T and get phi, and then from that we can infer our time delay distance and subsequently the Hubble constant. So the advantages of this method is that it's based on simple geometry and well-tested physics, and it provides a one-step physical measurement of a cosmological distance. So the method has been known for over 50 years. It was first proposed by Refsdal in 1964. However, getting each of these three things has been a challenge. Nonetheless, in the past decade or so, there's been a lot of advances in getting each of these three things accurately and precisely. And it's with these advances that my collaborators and I have started the Optical program. So Optical stands for H-naught lenses in Cosmograv's wellspring. So the goal of this program is to measure the time delay distance to each of these 5 strongly lensed quasar systems that we have, and constrain the Hubble constant to better than 3.5% precision. So here are the holy towers, who I can owe many of my thanks to. There's several people in California, lots of us in Europe, and a couple of people in Japan. So the goal of Holy Cow is to establish time delay gravitational lenses as one of the best cosmological probes. So shown here is the current status of the Holy Cow program. So the analysis of these three lenses have been completed, and these two, we're currently analyzing them. And in the next few slides, I will show the results from this most recent analysis of HCO 435. First thing we need, the time delays. So the Cosmography collaboration, which is led by George Milan and Frederick Urban at EPFL, together with the collaborators here, they've been carrying out a heroic monitoring effort to get the time delays of these lens quasars. So Cosmography stands for Cosmological Monitoring of Gravitational Lenses. So the collaboration has been using a network of small optical telescopes across the globe to monitor these flickering patterns of the quasar images and They've been doing it since 2004, so for over a decade now. And the expectation is to get time delays with a few percent uncertainty for about 10 lens systems. So shown here is the beautiful light curve that Cosmography has obtained since 2004. So shown, this is for the system above. A, B, C, D are the 4 images of the quasars. So you can see the pattern, the variability of each of the images over time in the past 13 years. And with this kind of exquisite data, we can almost measure the time delays by eye. You can see these features that are reproduced in all of these 4 images. So Vivian Bonvan, who is a PhD student in Lausanne, has used the state-of-the-art curve shifting techniques built by Multitivis and measured the time delays with 6.5% uncertainty for this strong lens system. I'd like to also mention there are also independent efforts to get the time delays. So there's the 9-step network, it's a for microlensing network for the detection of small terrestrial exoplanets, where there's also a quasar monitoring campaign as part of the collaboration. So recently, people here, so Giannini and collaborators, they presented the monitoring from this survey for 2 lens quasars. Here's one of them. This is a 2-image system, 047 of image A and B, and this is the light curve they got. And for this kind of monitoring, Giannini and collaborators have measured the time delay for this system for the very first time. So with the monitoring by Cosmography and MyStep and other independent monitorings, we can now get time delays with a few percent uncertainty for each quasar lens. So the next thing is to have to quantify the mass structure along the line of sight. And this is for the field of view, 3 arc-minute by 3 arc-minute field of view of 0435. So previous studies have shown that 0435 actually has a lot of nearby mass structures at different redshifts. So we have carried out a spectroscopic and photometric monitoring campaign to measure the redshifts of all the massive galaxies near the lens system H0435. So here's the box here. This is the zoom in, and this is our lens system. So all the objects that are marked in colors, these are all the objects, except for the star symbol. All these circle-colored objects are ones that we actually have spectroscopic riches for. So we're basically triple the number of spectroscopic riches available. And from our multi-band wide field imaging, we can estimate the amount of mass associated with these galaxies and use the number density of these galaxies together with numerical simulations like the millennium simulation to quantify the amount of external mass distribution around the system. And our spectroscopic campaign has importantly gave us spectroscopic redshift for the nearby massive galaxies around our lens system. This is important because the lens here is at a redshift that is different from the redshift of the nearby perturbers. So we actually have to account for this in our lens mass modeling. And that brings me to the next step. So our lens modeling, we do it with GLEE. So GLEE stands for Gravitational Lens Efficient Explorer. It's a software that Alexi Optical and I developed together. So how it works is that we model the mass distribution of the lens galaxy using parameterized profiles and also for the light of the lens. So essentially what we want to do is to use the images of the quasars and also the Einstein ring that we see. So this is coming from the host galaxy of the AGN that is lensed into a ring. So from this lensing information, we can constrain the lens mass distribution and get that potential to convert the delays into a distance measurement. So we need to model the mass distribution of the lens. We need to model the light of the lens in order to extract the host galaxy. We also model the light of the AGN, the light of this host galaxy of the AGN on a grid of pixels to allow flexibility. We also include the time delays. And recently, we have developed a new method to reconstruct the pointer function from the data directly, and also to include multi-lens plane modeling because there are nearby perturbers at different redshifts. So if we do all of this, this is the reconstruction distribution that we have obtained. So this is the top panel are the HST images of the system in 3 different filters. And the bottom panel shows our reconstruction. So this model was done by Kenneth Wong at NAOJ in Japan. So as you can see, we reproduced very well the global features of the system to measure to get the time delay distance. So a crucial part of our analysis was that it was done blind. So what this means in practice is that we don't look at our result in order to avoid confirmation bias. So because usually if we think, if HR is around 70, there's this tendency to confirm what we expect. So in order to avoid that confirmation bias, during the analysis, the cosmological distances and parameters are actually all offset from the median, that is, they're blinded. So shown here is a probability distribution of the effective time delay distance, and it's blinded. So the different color curves, each of these corresponds to a systematic test in our mass model. So we've tested several different systematic effects that we know of. And these are plotted relative to the median of the fiducial model. So we don't know where where the distribution is centered, but we can use the shape of the distribution, the width of the distribution, to test our analysis without biasing us because we don't know where it's centered.
What are the units?
These are megaparsecs. Yeah. So the collaboration agreed that when we unblind, we would publish our time delay distance without modification. So this was very stressful because we need to make sure that we don't make any mistakes in this analysis. Don't embarrass ourselves with a negative time delay distance, for example, when you unblind. And this took a lot of effort and time from the collaboration. But then last May, we had a face-to-face meeting where we're near the end phase of our blind analysis. So at that, we had scheduled an unblinding telecon on June 2nd. So at this unblinding telecon, we presented all the analysis we have done, the blinded results that we got, all the various tests, and there was a heated discussion from the collaboration. But at the end of the telecon, we actually concluded that we were not ready to unblind because there were still a few things that we were not sure of. So we rescheduled the unblinding party for 2 weeks later, June 16th. And during these 2 weeks, we worked like crazy, tried to do these last tests, and then we reconvened 2 weeks later, talked about these results of the final test that we did. And actually, all of us were pretty happy with the tests that we've done, with the analysis that we've done. And here are the unblinded results at the top. So this is now the unblinded, so no longer offset from the zero, the effective time delay distance. And fortunately, it's not negative. This time delay distance of this system is around 2,600 megaparsecs. And we provide an analytic fit to the probability distribution with these fit parameters so that anybody can actually use this distance measurement and combine with their favorite cosmological probe. So with that time delay distance measurement, and also from the previous 2 lenses, so we can actually measure the Hubble constant under this distance into h naught. So here we assume that we're in flat lambda and the different colored histograms are the distribution for h naught for the 3 different lenses that we have analyzed, and these are the corresponding median and 1 sigma uncertainty of the 3 lenses. And after checking that these 3 lenses are statistically consistent with each other, given their uncertainties, we then proceeded to combine these 3 measurements and obtain h naught measurement of 71.9 plus 2.4 minus 2.0 from the 3 lenses that we have, and that's given by the black histogram. So shown here is the plot that I showed at the beginning of the talk. So this lensing point was actually from 2 lenses, from Holy Cow and Cosmic Grill. And now we are here with 3 lenses, and with uncertainty constraining cosmology. In particular, the spatial curvature of the universe, number of effective neutrino species, mass of the neutrinos, and dark energy accretion state. So each one of these is the cosmological factor plotted against H0. And I'd like to bring your attention to this gray contour. This is the 95% confidence region from CMB observations. So the bigger one is from WMAP, and then the smaller dash one is from Planck. So notice that once you relax from this flat lambda CDM model, the CMB gives you a strong degeneracy between these curvature pattern, neutrino pattern, and dark energy with H0. So there's strong degeneracy here. And the solid contour, this is the results from our 3 lenses, which mainly measures H0. So you can see our constraints are nearly vertical. And it is a combination of this H0 that's vertical that breaks the parameter degeneracies in the CMB data for constraining much more tightly the spatial curvature of the universe to be spatially flat, and also placing much tighter constraints on the effective number of neutrino species and also dark energy frequencies. So looking forward, we still have 2 more holy cow lenses that we're analyzing, these 2. And this is the image with the lens galaxy subtractive revealing the Einstein ring. That's important for us to model and constrain the lens mass distribution. We have actually 4 more doubles or 4 more 2 systems with HST data. This was observed in HST cycle 20, We have follow-up data partly in hand and partly pending. This is for the wide field imaging, velocity dispersion of the lens, spectroscopy of the field. So the expectation from holy cow after we analyze these 2 is that we will get uncertainty with better than 3.5% H0 for most cosmologies, with W of -1. So our initial HST proposal, when we started this program, we actually aimed at 3.8 from the whole sample. But we actually achieved this with just 3 of the 5 lenses. And this is really thanks to the great efforts of holy cow that the great efforts of Cosmography that has been monitoring these quasars for over a decade and with their improved time delay measurements. So far, the holy cow sample and the next lenses are really the best quasars that we have. So to really move forward, we need more lens systems. So how do we do that? Well, there are several ongoing wide field imaging surveys, including the dark energy survey, hypersuperincan survey, and the kilodegree survey. So each of these surveys are going to cover more than 1,000 square degrees. So thousands of square degrees combined from these surveys, and they're all ongoing at the moment. And from these imaging surveys, we expect to get more than 1,000 lens quasars, which is really exciting. But then the challenging part is how do we find them with the ground-based imaging. So up to now, I've shown you beautiful, high-resolution Hubble Space Telescope images that look like this, where by eye you know this is a strong lens system. Background source is lens into A, B, C, and D by a full ground lens galaxy. So with the HST image, it's very clear and obvious. But this system, the same system observed from the ground, looks like this. This is, so all of these features are blended together due to the atmospheric distortion on Earth. And this is with Subaru, which is an excellent site with excellent seeing. So the image quality of this was like observed with 0.5 arcsecond seeing. So even with excellent seeing, it's still very hard to tell that this thing is actually a strong lens system. So how do we tell if this is a lens or not when we see it from these ground-based imaging? Well, the way is to use the configuration of blended images and lens model. So the multiple images of the quasars, they don't just appear in random positions around the lens. There's certain specific configurations that they must be in if it's a lens. So the 3 generic configurations we have are the cross, the Einstein cross. So here the lens galaxies are the 4 quasar images are symmetrically around it, like the over 3.5 that I showed. So this is the Einstein cross. Another typical configuration is to have 3 of the quasar images very close to each other, and then the 4th one on the opposite side of the lens. This is called a cusp. And then finally, there's the fold, where two of the quasar ridges are closed, and then you have the third and fourth one on the other side. So basically, these are the three generic configurations of lens systems that you can have. So if you're given an image, a ground-based image, you can try to see if these blended blobs match these configurations. So as advocated by Phil Marshall for several years, for a system to qualify as a lens candidate, it must be explained by a plausible lens model. So there's several ways to go about this. One is to do direct modeling. So this is Lens Tractor that is developed by Phil Marshall and collaborators, where they classify objects based on explicit model comparison. It's the Bayesian framework. There is CHITAH, and its classification based on simple lens model fitting. So I'll describe a bit more about this method. There's machine learning, where the implicit lens model actually enters via the training set. And there's fun things like citizen science, where citizens, they can visually identify lenses after they're familiarized with the generic lens configurations, like what we saw on the previous slide. So these are the different approaches to finding lens quasars from the ground. So I will tell you a bit more about CHITAH. This is a new lens hunter for strongly lens quasars. So all these ground-based imaging surveys, they're observed in multiple filters, which means that we have color information. So given an object that looks like this, we can use the color information to separate out possible quasar features and possible lens galaxy features. For example, here we can use color to separate out the blue things, which are possible quasar features, and the red thing, that's the possible foreground galaxy. We then fit positions to the blue features, point sources, and then we see if these point source image position can map to the same position on the source plane, as it must be if it's a strong gravitational lens. If we can do this, then it is probably a lens. So on the right here is another object where we do the same thing. We use color information to separate out blue features from orangey features, and then we fit for the positions of the blue features, but there's no math model that allow us to map these four positions back to the same position on the source plane. So in that case, this is probably not a lens. So this is how we can use lens mass modeling to try to classify whether an object is a lens or not. So James Chan, who is a PhD student in Taiwan, has worked with me, has developed an automated and fast algorithm to use multi-pad imaging for lens classification. So since this method was developed in Taiwan, we have a name for it in Mandarin. It's 重力和影像探讨法, which means robot for the exploration of gravitational imaging. So for those of us who have who need some help with pronunciation, here's the direct transliteration of the robot's name. So 重力和影像探讨法. So from this we built an acronym, CHITAH, and that is our Euclid lens hunter. So we have tested CHITAH with mock lenses and also real systems observed with the Hawaii telescope. Legacy surveys are shown here are different mock systems in different brightness and image separation, and then these are real systems from the CHITAH legacy survey. So basically, after testing this, we find that CHITAH does very well. So on bright, large separation lenses, we can get greater than 90% true positive rate and less than 3% positive rate. And we're currently running CHITAH on HSE and DS surveys to find new lens systems. So in the next slides, I will show you some of the new lenses found in these imaging surveys. So the DS this is the first lens quasars found in the DS survey by Anomalous and collaborators. So they discovered these two lens quasars. These are the 5 filters in DS, and this is the color composite. And these are the two spectra of the two systems showing the two images in different color, one in blue and one in purple. And basically the spectrum of the two images are identical, confirming that it's a strong lens quasar system. So there's also been ongoing effort to find new lens quasars. In the SDSS BOSS survey, so Anomalous collaborator discovered 13 lens quasars in SDSS from the spectroscopic quasar catalog from BOSS, and in combination with the morphological and color information from the SDSS imaging. So here are the 13 new lens quasar systems from SDSS BOSS. Actually, all of these are two image systems. So in general, there are more two image systems than four image systems. In HSE, though, we found our first four-image system. So this is found serendipitously by Anomalous. And the quasar images are these four that you see. Well, actually, these are, it's currently still a bit unclear whether this is really a lens quasar or not. It's at a very high redshift, close to 4. It's likely a lens quasar, as lensed by the foreground galaxy. And if it is really an AGN, this is the highest redshift quad AGN known so far. So once we find these new lens quasar systems, in order to use them for cosmology, we need to model the mass distribution precisely and accurately. And to do that, we really need the high resolution imaging to reveal those Einstein rings coming from the AGN host galaxy. So until now, this has meant Hubble Space Telescope observations to get these high sensitivity and high angular resolution imaging. But sadly, Hubble is great, but it's not going to be there forever. So one really needs to have an alternative to Hubble Space Telescope. And the alternative is to use ground-based adaptive optics imaging. So shown here is an illustration of how AO works. So here's light coming in from the telescope. The wavefront of the astrophysical object is distorted due to our atmosphere. And then here it bounces off a mirror and goes through a beam splitter. Part of it goes into a camera. Another part of it goes to the wavefront sensor. And then from this control system, it senses the shape of these wavefronts and then tries to adjust the shape of the mirror, adapt the mirror, so that the distorted wavefront gets corrected when it enters the camera. So here is an image of a star without AO system. So you see that it's, the image is highly distorted due to our atmosphere. And this is once you turn on the AO. So this is in 3D. So once you turn on the AO, you get a much sharper focusing of the background star. So with a perfect AO system, you would actually reach the diffraction limit of the telescope. So all these 30-meter class telescopes that people are planning and building rely on this AO technology. So here is an example of the AO observations obtained by Keck Observatory in comparison to the Hubble Space Telescope imaging. So this is actually obtained as part of the SHARP program led by Chris Fosnack. And as you can see, we're getting the angular resolution-wise, it's actually very cool, even better than HST because Keck is 10 meter, whereas Hubble Space Telescope is 2.4 meter. But this is from the ground, so there's atmospheric distortion. Once you correct it for that, you can in principle get even higher angular resolution than HST. But then the challenging question is, can AO data actually produce similar cosmological constraints as Hubble Space Telescope data for time delay systems? And the main challenge here is that we do not know the point square function of the AO system well enough. So the point square function will spread out the light from the quasar. So the quasar light outshines the light of the ring, typically, the host galaxy of the quasar. And we really need to know the point square function accurately in order to extract the ring for our lens mass model. And not knowing the point square function in advance is a challenge. So to overcome that, so Zhifan Chen, who is a master's student in Taiwan, worked with me, and now he's in Davis. So he has developed an iterative point square function reconstruction technique that simultaneously reconstructs the point square function and the lens mass model. So here that I created using this input points per function. And this is the image that I sent him to define. I didn't tell him what the input PSF is. So I just gave him this, and then he ran through his new modeling technique, and this was his modeled image, and this was his reconstructed PSF, which actually globally reproduces pretty well the input. And if we look at the parameters, so if we look at, compare the AO constraints to the HST constraints of the one system that we have both AO and HST. Most of the parameters are recovered for the key lens parameters, in particular the time delay distance. So the black contour, not the black, the white solid contours are the constraints from AO, and then the dashed red are from HST. So AO imaging is a promising approach to follow time delay lenses for cosmography. So so the ground-based AO is great, but then we will soon have JWST, James Webb Space Telescope, that's scheduled to launch 2018, next year. And JW will be fantastic. So Moe and collaborators simulated JWST near-cam images of different lens systems shown here. So there are faint ones, faint systems, and then bright ones. And then they modeled these systems to see what the necessary exposure time to get the signal to noise required for modeling these systems for cosmography. And they find that these are the typical exposure times. Basically a few minutes each. So you only need a few minutes of JWST observations per system to achieve the required signal to noise for lens mass modeling. So until now, for time delay cosmography, I focused on lens quasars, because these are the ones where the quasar light is changing over time. But in principle, any source that changes over time, you can measure time delays. And a really exciting time is strongly lensed supernova. So supernova is very rare. Strong lensing is also rare. The chance of one of two other. So to have a strongly lensed supernova, one really needs to be lucky. And in fact, Pat Kelly and collaborators were lucky. They serendipitously found the very first strongly lensed supernova in this galaxy cluster, MAX 1149, back in November 2014, as part of one of the surveys in glass. And shown here, this is an image of the galaxy cluster. These blobs here that you see, these orange blobs, these are the cluster members. So this is in the lens. And if you look closely, there's a background source. So this there's a spiral galaxy behind the cluster that is lensed into three images. So one here, and there's a zoom in. Two, and that's the zoom in. And then the third one up here, and that's the zoom in. So this background spiral galaxy is lensed into three multiple images by this forward cluster. And if we look at this image in particular, there's actually a cluster member that is sitting right on top of the spiral arm of the spiral galaxy. And this further lenses the spiral arm into multiple images. It's pretty spectacular. So in the next slides, I'll focus on this panel. Shown here. So this is the observations of that panel in different HST filters before 2014 at the top, and this is observed in November 2014. So if you take the difference between the first two rows, this is the difference image at the very bottom. So you see that there's these extra point sources that happen around this cluster member. So this is actually a supernova that happened in the spiral arm of the background galaxy, and that's getting strongly lensed. So there's four images, S1, S2, S3, S4. So this is the very first spatially resolved supernova, strongly lensed supernova. So now the exciting question is, there's one image of the spiral galaxy here, but it also appears here and here, which I'll call image SX and SY. So if the supernova appears in this galaxy, in this image, it must also appear at some point in SS and SY because they're the same images of the same spiral galaxy. So this actually now provides a great opportunity to perform a blind test, meaning modelers can try to predict when these images are going to occur and then observations can then try to confirm that. So, the preliminary models based on existing data at the time of discovery, those models were quite uncertain. The delay of this, time delay of this one was actually negative, meaning that the models at that time predicted this happened more than 10 years ago before this image. So since it happened in the past, there's no chance of observing it. But this image, SX, should happen between 1 and 10 years after this. So 1 and 10 years is kind of uncertain, which is making it very difficult to follow it. So then several different teams got together to try to get better data of the cluster, both spectroscopic and also from HST frontier fields and the glass observations, with these better data to improve on the model and to try to predict better when the next image, SX, would happen. So here are the different, so the different teams actually shared this data, and different modeling teams that try to predict when SX is going to happen, and this is shown in this plot. So SX magnification ratio relative to the first image, S1, and this is the time delay, SX relative to S1. So 1 year will be around here, 300 days, 365 days. And the different points, colored points here, are the predictions by the different teams. And this is done before SX was observed. So people really worked hard to try to get these predictions out in order to then follow up the appearance of SX. And I'm on the modeling team that's led by Grillo, so that's the red point. And most of these points actually show, so this prediction was done in October 2015, so about 1 year after the SX, because the proof model at that time predicted that it could happen in 1 year, so we really tried to rush to get a prediction done within the year, and we managed. So here's the predicted, and we predict, so most of the models actually predict that the detection of SX should happen before the end of 2015, right? Because 1 year is here and most of the points are sort of to the left of that. So HST, the cluster was visible again in October, late October, so HST pointed at it, but then there's no image of SX. Then in November 2015, again HST pointed at it, and there was still no image of SX. So at that point, we modelers are getting very nervous. Some models actually have been sort of ruled out at that point, and Claudio and I were like starting to think, oh darn, what could have gone wrong with our model? But fortunately, in December, we got an early Christmas present that year. So here's an image taken in mid-December, and this was an image from April where there was no image of SX. And shown here, you see there's an image of SX up there. So it's the image SX appeared in mid-December. And based on that detection, that actually puts a constraint on the brightness of SX and the time delay. So the contour here is the 1 sigma and 2 sigma constraint based on the observations. So 2 models did quite well. So there's one, the green point here, following this constraint. This is a model done by Masamune Oguri, team in Japan. And then the red point is our team, led by Claudio Grillo. And in particular, this was actually predicted with green, the model that we use for time delay cosmography that demonstrates the robustness of our modeling approach. So, in addition to predicting just the time and brightness, we can actually predict the location as well. And these circles are the different model predictions before SX happened. So our team here is the one highlighted in green, Grillo team, and then the other 2 teams are shown in red circles. And the red cross, this is the actual detection. So we're actually able to predict the occurrence of SX within 0.2 arcseconds. Here's the slope of 2 arcseconds. So our team was able to successfully and precisely predict all 3 observables of SX: time, magnification, and location. And this relied on GLI, software that Alexei had developed, which was able to do this because we can reconstruct the entire supernova host galaxy, so using all the pixels there, which provides a very accurate clustering and prediction and predicts the appearance of SX. So that was last year, well, 2015. Then in 2016, a few months ago, we got our second lens supernova. So this was discovered in the IPTF team, and this time, the previous one in this cluster, this is a core collapse supernova. And this recent one, discovered by Heidelberg and collaborators in the IPTF team, is a type 1A supernova, which is great because type 1A we know is a standard capital. This is the very first strongly lensed type 1A supernova. And here are the three Hubble space, the three HST images in different bands. And the bottom panels are the adaptive optics imaging. So the white circles here pinpoint where the four supernova images are. And when I first saw this with my collaborators, I was very interested to know what is the time delay like. Can we actually use this for cosmography? So then my collaborators and I, we tried to model this system to predict what the delay would be, which would also help in monitoring the system to get the time delays. So shown here, this is the HST image of the system. And this is the model by Anukita More and Hasan Lugari using graphic. And this is the model that I got with Euclid. And this is the residuals, so the difference between the model and the data for the graphic. And I believe so we're able to model pretty well the system. And this is the reconstructed host galaxy of the supernova that we get from Euclid. So the supernova is appearing as where the magenta star is. So it's kind of a funky shaped background source galaxy. So with this model, we can actually predict what the delay would be, but unfortunately we find that in all of our models, the maximum relative time delay is actually very short, less than a day, which makes it kind of challenging for the follow-up. And another peculiar feature we found was that the fluxes of the multiple images of the supernova predicted by our model, shown in the white solid circle, actually don't match what is observed, which is the open symbol here. So these are the brightness and the magnitude of the image of the four images A, B, C, and D. So the model predictions are white, and then the open science symbols are the observed. So this offset is actually pointing at a possible microlensing of the images by the stars, which could further complicate the time delay measurements. Nonetheless, it's really exciting that we have our very first strongly lensed type 1A supernova. So all these wide field imaging surveys coming up like LSST will really change this. So stay tuned for the results of the monitoring and follow-up efforts by the IPTF team. So we'll be getting HST time to monitor the system. So what are the future prospects of this approach? Well, experiments and surveys in the 2020s, including Euclid and the Large Synoptic Survey Telescope, LSST, they will provide around 10,000 lens quasars and around 100 lens supernova. So this is the forecast done by Ordinary Marshall. So Euclid here is a space mission that will be great for discovery, imaging, also for the spectroscopy. And LSST is a cadence imaging survey. It's going to observe the entire southern sky every few nights, so 20,000 square degrees every few nights, making a movie of the southern sky essentially for 10 years. And this will be great for discovery. And because it's cadence surveys observing every few nights, we can get the time delays from this for free. And also the LSST will have great imaging. And then there's JWST, schedules for long, that will give us the high resolution imaging and spectroscopy. So with these upcoming experiments and surveys, time delay cosmography as a feature. So here I conclude. So time delay distances in Delta T of each lens can be measured with uncertainties of around 5 to 8%, including known systematics. With the three lenses that we have in Holy Cow, H0 is around 71.9 plus 2.4 minus 2.0 kilometers per second to make a parcel in flat light. 90% precision measurements independent of any other probes. Search is underway to find new lenses in HSC and DES. So stay tuned. There's actually going to be a lot of new lenses coming up from the DES collaboration. AO and adaptive optics and JWST imaging will be efficient for following up lenses. The first strong lens supernova, which was called Supernova Refsdal, blind test demonstrated the robustness of our cluster mass modeling approach in our software lead. The first strongly lensed type 1A supernova discovered by the IPTF team, but the delays are very small. Current and future surveys will have thousands of new time delay lenses providing an independent and competitive field of cosmology. Thank you.
Thanks for the beautiful talk and for the explanation of these deeply beautiful acronyms that you have in this field. There must be many questions. Please go ahead. Yes.
You have a big survey like quasar is you could not only search for lenses dedicated to use. I mean, what you would like to have is not just a strong lens, but one whose time delay you can nicely measure. So, in addition to searching for multiple image configurations, you could also search for such image configurations which belong to the suitable object. Would that give you a higher detection rate or more efficient search?
So in some sense, they're correlated because you can measure time delays better if the quasars are brighter. It's easier, the photometric also will be more smaller. So, and brighter quasars are easier to detect as well.
I was thinking about these nice quadruple images, which are beautiful to look at, but have very small angles.
No, not really. The symmetric one has small delays, but the fold and the cusp don't necessarily have small delays. So those ones are actually better for cosmography. If I have lots of lens quads to pick from, I will pick those ones. The folds, the non-symmetric ones, they actually provide more information on the mass distribution.
Could you pre-select for those right away?
Well, right now the main problem in this challenge is that just finding any lens creators. So we don't have the luxury of selecting. Yeah, it's changing, but it's still a pretty hard game. In trying to find quasar systems from the global groundings imaging.
So, people already come up with ideas how you, if you have something like this LSST survey, have people come up with ideas how you could automatically detect lens supernovas?
So there's a recent paper by Goldstein and Nugent, who proposed a method to try to detect lens supernova by looking at the brightness of the supernova. So basically the idea is that if it's lensed, then it will get magnified. And if it's strongly lensed into multiple images, the flux that comes from the supernova will be much brighter than it should be because of the effect of lensing. So they proposed a method to look at the flux of the supernova and see if it's compatible with the redshift of the lens galaxy. And if it's much brighter than the photo Z of the lens, then it's likely to be a lens supernova. So this is one of the methods that's recently proposed. Until now, there hasn't been that many methods because it's quite new. It's only until now that we actually have the survey area and the cadence needed to find the system. So far, the first two are, the first one is completely serendipitous, just from monitoring a cluster field. Second one was found by IPTF, again, it's a large cadence survey. But it's a new, relatively new field.
Yeah, I was wondering if there's any prospect of getting some spectroscopic information on these multiple design delay in one shot?
I think there is information from that, indeed. If you take a spectrum, and because you know like you said, the supernova light curve evolution, that allows you to put some constraint on, like so
Sure.
if we take a spectrum and then get the spectrum of these two, they will look different because of the time delays, and that can give you some information. But it depends on how uncertain, like how well you can pinpoint the time of explosion, time since explosion from each spectrum.
I guess it's not so similar because you've got temperature changing and you've got line ratios changing, and this goes in one direction.
Yeah, I think this has not yet really has not been looked at that much, at least.
I'm presuming that things like this you can't do that, so just do faint. But I mean, when you get, ELT and things like that, you have a huge variability in spectrum. Might be an interesting project for ELT.
But I think they're not that faint. They can. This is well, this one is very faint, but I think like the LSST forecast that Oguri and Marshall did, the magnitudes were like 20, 21 or so, 22. Sort of at the limit of the current telescopes, maybe, but still feasible. But this is something to look more into. It's still a relatively new topic.
So, can I also intersect the question? So, as I understand you, your results are more in line with the recent results. So, that means the cosmic microwave background results are still discrepant to this 1 year data. Can you speculate what is the most likely reason for this? Is some trends that becomes visible now?
I think at the moment, the tension is actually starting to become significant. So this is now really interesting. But what is really the cause? Like, is it more relativistic species, or is dark energy not equal to lambda? I think we need better constraints on H0 to really know better which possibility.
Couldn't people explore the implications of this one, say the W to give it some other value that they could change other cosmological parameters? Can you do consistency checks?
So right now, so this is one of the plots that I showed. So we did try to do this. Right, so the constraints from the CMB are the gray contours. This is relaxing now for flat on the CDM. And if the H0 is higher than Planck value, basically, for example, on W, dark energy, you need it to be more negative than -1, or you need, so basically these kind of contours tells you the deep, like the possible deviations from lambda CDM in these constraints.
But things like so the origin of the elements and stuff like that, would that be changed? I mean, some parameters must be sensitive to that, and some must not.
I have to think about that.
I mean, if one thinks of, let's say, the number of neutrinos and things like that, that must be sensitive to these other constraints.
The number of neutrinos is, it is sensitive to that constraint.
But yes.
As you know, I'm a firm believer of the whole constant value 1608. Now, E1608 comes very close to that. One of the others are higher. Is there any reason why 1608 is substantially lower, right?
I think they're all it's a statistical scatter.
So there's nothing peculiar in the model?
I don't think so, yeah. So basically we built our modeling technique based on 1608. So that was our very first system where we did a lot of work to build up the pipeline. And then we essentially applied the same technique to the other two lenses. basically that's currently very scattered and it's due to uncertainty. It's expected given the uncertainty that we have.
So just as
Yeah. At the moment, we don't see any systematic uncertainty. We don't detect it at the level, given the level of our measurement uncertainty. If the two distributions are totally off, then yeah, we know something is wrong. But currently, the statistical consistency.
To what extent is the lens model actually terminally, considering that the lens may contain vertical?
Yes, so we try to model the mass distribution using different profiles. So power profiles, dark matter plus baryons. So we use these different models to quantify our uncertainty. And for the mass modeling, another way is actually to even, because we have all the pixels in the ring, the Einstein ring, there's a lot of constraints. We actually even have a pixelated mass reconstruction approach, which essentially doesn't depend on a mass profile. And there we actually find that the correction, this pixelated correction is very small. So the mass distribution tends to be rather smooth. So all of this is incorporated into our uncertainties. And we also have stellar kinematics of the star of the lens to further constrain our lens mass distribution, to break lens model degeneracies. Because there is lensing degeneracies that we get additional data to break out.
Okay, I see no more questions. Before we thank Sherry again, two more announcements. Next week we have Ephemesis from Oxford speaking, talking about their efforts in modeling galaxy formation and evolution. And as usual,